Okay, physical science time. Today we're going to talk about radioactivity. 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 And then you can draw a fancy little swirly underneath it like some of us did. We're going to review, as I said a second ago, we're going to review the four fundamental forces of the universe first. So in order to do that, let's list them, and let's list them from the strongest to the weakest. So what should I put first? What will my first diagram be? There's a confusion. What is the actual right answer? The strong nuclear force is the strongest. Strong nuclear force. What's the second strongest force of the universe? Electromagnetic force. What's the third strongest force of the universe? Weak nuclear force. And the weakest force of the universe is? Gravity, or the gravitational force. Let's put gravitational force. You can put whatever you want. I mean, this is your notes. However you want to learn it is fine with me, as long as you're actually learning it. But in order to keep them the same format, we're going to put force for each one, or I'm going to put force for each one, I should say. Are there other forces in the universe? Like what? Friction is just the electromagnetic. Really, that's what I get at. There are other names of forces, but these are the only ones that exist. We name them other things. For instance, if I'm mad and I push them down the stairs, which of these forces is that? None of these is push a freshman down the stairs. Okay, gravity is causing them to fall down the stairs. Yes, so that's true. But which one was my push force? Was I pushing them with gravity? I was using my mass to attract their mass? No, so it wasn't gravity. Which one was it? It was the electromagnetic. Yeah, what's actually happening when you push something is the electrons in your hand. Every atom in your hand has electrons. And those electrons can't occupy the same space as his electrons. Why? No. Why can't they be in the exact same spaces? Well, for one thing, there's a physical rule against things being in the exact same space, but they're not even really touching. As my electrons get close, pretend my hands are microscopic and they're electrons. As my electrons get close to Peyton's electrons on his shoulder, apparently he's the freshman I'm mad at, what happens to them? They can't collide. Why? Yeah, they repel, exactly. So on the microscopic level, my electrons, when they get close to Peyton's electrons, repel, and that force is transmitted to him. So they're moving, and then these ones move. And that's a push. So you're never actually touching anything. Well, like if you get, you'll see some, I guarantee you sometime if you stay on TikTok or YouTube or something, Facebook or Reddit, you will eventually see someone say, you never actually touched something because your electrons are always repelling. That's not quite true. Like if you put your hand in some glue, the glue forms bonds with your hand. That's why it's sticky. And so really, as much as anything can be touching, that's touching. But no, all of it is the electromagnetic force, you're right. So what we think of as probably our normal daily forces are either gravity or the electromagnetic force. Do these matter? Yeah, the universe will literally fall apart without this one, and it wouldn't be the same without this one. We need all of them, but these are the two we deal with on a daily basis. So what's the strong nuclear force do? Right, and not only that, but first of all, what it does, the most microscopic thing it does is keep the quarks together in a nucleus. Remember that? So if we have two up quarks and a down quark, and they're held together by the strong nuclear force, this forms a what? I said two up and one down. A proton. This forms a proton. Oops. Come back. And then maybe, I outlined it in red. Here my red is representing the strong nuclear force. And now I have two downs and an up, and they're held together. This is a neutron, and they're held together with the strong nuclear force. And this proton and this neutron are held together with the strong nuclear force. What atom's nucleus have I just drawn? Not just say its whole name. Hydrogen. No. Hydrogen 2, because it has two massive particles. So anyway, so that's what the strong nuclear force does. It's the glue, the fundamental glue that holds together. In fact, we call the mediating particle of strong nuclear force gluons because it glues these things together. It glues the quarks together, and it glues the nuclear particles. This is very important for what we're talking about today, so we're going to come back to that. The electromagnetic force, how can we diagram the electromagnetic force? I'm sorry. Sure, yeah. We could draw two electrons repelling. Here are electrons, and they are repelling because they're close together. Could we draw another thing that would diagram it? I mean, this is not the whole story for the electromagnetic force. We could draw that. I'm going to keep it on a subatomic level just for this one, and we're going to draw a proton and an electron, and what are they going to do? Are they? They're going to attract. Make sure you... I think you do know the right answers to these things. Just make sure you say the right answer when you say answers. These are going to attract. I should make that a little bit clearer. Because I drew the exact same arrow between them. These are going to repel because they're the same charge, and these are going to attract because they are opposite charges. Okay? How can I draw the weak nuclear force? I'll be very impressed if you know. Do you know, Rhett? Yeah, I mean that's a good start of a simple explanation. What they do is they cause a proton. It can do either of these things. It can cause a proton to absorb, or I'm sorry, I'm going to put release. It's cause a proton to release something called a positron, which then turns into a neutron. What color did I draw neutrons a second ago? I don't think I did. I think I drew the protons. I'm going to have to find it. Neutrons here are Heinz 57 sauce. There we go. Thanks, Justice. So it can cause a proton to release a positron, which makes it become a neutron, or it can cause a neutron to release an electron. No, they don't contain them. This is one of the fundamental forces. It just does it. It's like magic, except it happens all the time, and we kind of understand it, so it's not really magic. And then that becomes a proton. They don't contain electrons, but a neutron can release an electron, and that becomes a proton. And that's what the weak nuclear force does. You know what? They're all on the ground. And then what does gravity do? Yeah, any mass in the universe, mass, anything with mass. A duck, the earth, the sun, your mom, a houseplant, all of these things have mass, and so all other things in the entire universe are attracted to them. Why does not everything just form into a big lava lamp blob in the middle of the universe then? Okay, because there are other objects attracting them in different directions, for one thing, and also because this is, while it acts over the longest range, it still does have a range, you know. There's an attraction between these, but it gets weaker the further away they get. So even though even though Mars has a much greater mass than the flagpole, you're more strongly gravitationally attracted to the flagpole than you are to Mars because Mars is so much further away. But why don't you just shoot over towards this flagpole? Why aren't you attracted to the flagpole? Because of what Peyton said, because the Earth is more massive and it's closer, and we're attracted to that instead. Mass. This is the third time this year that we've talked about this. Why do you think this is important? This is, I mean, really, this is everything of physics and chemistry and biology and psychology. Everything is this. This is the way our universe works. This is in simple little children's or simple half-stupid science teacher drawings. These are the way the universe works. This is everything. It gets more complicated the more stuff we add, but everything is described in these four little pictures. So let's erase some of these and move on to we're going to talk about the strong force, and we're going to talk about that. What does all this have to do with radiation, Mr. Keim? You might be asking yourself. Well, I'm about to elucidate that point for you.
What fundamental force was plasma?
Plasma is an object, or plasma is a...
Well, like, what would it be like?
Plasma has to do with the electromagnetic force and the strong force and gravity, and probably the weak force a little bit. But what you mean is that what's happening in plasma is that there's enough energy that the electromagnetic force between the protons and electrons that are normally in an atom, that electromagnetic force is overcome because everything's moving so fast, and so they separate from one another. And the attraction that would bind them back together is not strong enough because they're moving so fast. And that's simplistic, and there's more to it than that, but that's the gist of it. So the strong nuclear force exists primarily where? In fact, really almost exclusively. It technically, like all the other ones, technically permeates the entire universe. The universe is kind of like a layer of 4 pancakes. everywhere in the universe there's a field. If we look at the universe as a two-dimensional object, there's a strong nuclear force, a weak nuclear force, a gravitational force, and an electromagnetic force permeating the universe, not in that order. Everywhere in the universe, everywhere in our three-dimensional universe, these exist. And we can think of protons as excitations in the strong nuclear force field and in the electromagnetic field and in the weak nuclear force field, and the protons really permeate all of them. So a proton is kind of like a little lump that goes through all of them. An electron only interacts with the electromagnetic force and the strong nuclear, no, really just the electromagnetic force and a little tiny bit with gravity, so that's kind of like an electron. This is all to say that on the quantum level, they're like waves. If the universe is like a layer of 4 lakes, these particles are like waves in that lake, and some of them interact with all 4 lakes, some of them interact with only one. Anyway, that's kind of upper level stuff, but generally, the protons, which are interacting with the strong nuclear force and gravity and electromagnetism and the weak nuclear force, but when they interact with the strong nuclear force, that only happens noticeably on the nuclear scale. So if we have a very small nucleus like that one, the strong nuclear force is plenty small enough, or plenty strong enough to keep them together, okay? But if we start having a very large nucleus, where these are now protons, are purple, if we start having hundreds of protons and neutrons together in the nucleus, this is supposed to represent hundreds of protons and neutrons. What do you notice about, so these two, pretend they're smaller. On this scale, they would be like that and that. What's the difference of this and this? Yeah, which one of our CCCs is the difference between hydrogen-2 nucleus and this uranium-238 nucleus, for instance? Scale, exactly. There's a difference in scale. And what do we know about we know that gravity, even though it's the weakest, acts over the longest range. So what does that imply about the strong nuclear force? It's the strongest, so it probably, has a really short range. In fact, even a large nucleus like this, not even a large one necessarily, but a medium-sized nucleus, the strong nuclear force between this boy over here and this boy up here is almost non-existent, even over the tiny little range of an atomic nucleus. It's very, very weak. And if this is a proton, and I drew this as a neutron, but if they're both protons, what other force exists between them? Yeah, they repel because of the electromagnetic force. And that's weaker than the strong force, but it also acts over larger ranges. So at this range, the strong nuclear force is weaker than the electromagnetic force. Well, so what do they do? Over time, they explode. Yeah. So this unstable atomic nuclei fall apart due to the strong nuclear force and electromagnetism, or rather the lack of the strong nuclear force and electromagnetism. Your book does a neater job talking about this on page 537 if you want to turn there. I like mine better. I think it's cuter, but the book's is neater. It shows you that the protons attract protons with a strong force, neutrons attract neutrons with a strong force, and protons attract neutrons with a strong force. But there's electromagnetic repulsion between protons and protons as well. And that gives us a hint as to what neutrons do. The universe probably wouldn't exist as we know it without neutrons, because they do interact with the strong force, but they don't interact with the electromagnetic force. So they offer strong force attraction among all these particles, but they don't offer electromagnetic repulsion. Yeah? Do you have questions about this before we move on? So at its core, this is called radioactivity. This is what radioactivity is nuclei falling apart. And the stuff they emit as they fall apart is radiation, nuclear radiation.
Are we looking for a way to use that as power?
Oh, we already know the ways to use that as power.
Well, sorry, correction. Way to safely use it as power.
It's relatively safe. Anyway, some nuclei are unstable. Period. This causes nuclear. I want you to be specific at least most of the time and put nuclear radiation, because we also know another thing that we call in science radiation is electromagnetic radiation, and that's a kind of different thing. I mean, there is some overlap. Rays are caused by nuclear radiation, but they also exist on the electromagnetic spectrum. So there is overlap, but nuclear radiation specifically is talking about particles and energy radiating out from a nucleus. That's why we use the word radiation. So here's a nucleus. as the particles and energy radiate out, meaning they go from a center point and go outward, that's called radiation, nuclear radiation. Do you see the link between, like, for instance, your math word radius and this nuclear radiation? Do you see that link? Because they're radiating out. They're coming out from a central point, just like the radius of a circle comes out from a central point to the edge. I bet now you're very anxious to learn about what kinds, that's supposed to be the word what. Thanks, Justice. What kinds of nuclear radiation are there? I bet you're anxious to learn about. Let's start. I always think this is going to be faster than it actually is. So let's just start by listing them, and then we'll describe each a little bit more in depth later on. There are alpha, beta, plus, beta minus, gamma, electron capture, spontaneous fission. Is that 6? Yeah, that's already 6. Good job. These are their symbols. I'm going to name them next to them. Alpha, beta plus, beta minus, gamma, electron capture, and spontaneous fission. Guess what's going to happen with each of these things? That'll make it so you have to do a worksheet. Yeah, there's math. There's math with these, with most of them, and we'll do the math. These are the kinds of nuclear radiation. And what are they all caused by? That's more important than the math. What are they all caused by? Yeah, unstable atomic nuclei. They're all caused, great job, Hayden. They're all caused by unstable atomic nuclei. And what happens, do you think? Why? Why does this occur? We said unstable atomic nuclei, but what does it do for the nucleus when one of these things falls off of it?
Not good.
No? Well, it's not good for you if you're around it.
It can be good because it's a dying piece of it.
Okay, let's not use words like dying because that applies to biology and knowledge, but
Not dying, but it's
it makes it more stable. Okay, so think about this. You have a grand Lego set. Justice, I'm targeting this at you. Okay, so you build, for instance, Uranium 238. You build a 238-piece Lego set. And your brother, Hayes, comes in and smash it on the ground. And if he keeps smashing it, he smashes that one, and it breaks somehow. And then he picks up the broken pieces and smashes it again. Eventually, he's going to come to it gets more and more stable each time, right? It's going to break less and less each time. Eventually, it'll just be possibly individual Lego pieces, or maybe a set of 4 Lego bricks stuck together so well that no matter how many times you smash it, it's stable. Do you know what I'm talking about?
like
So
flat pieces that are getting stuck.
yeah, when these unstable nuclei decay, it makes them more stable. Eventually, there's a stable bit that just stays there, we presume forever. So these are the kinds of nuclear radiation that can occur.
You know when like those small Legos would get stuck together, you just had to use your teeth to get them out and stuff?
Yep, I know all about that. Okay, the other thing we need to talk about is what we call half-life. Half-life, which is abbreviated with the Greek letter lambda. Do you need more, before I just said lambda and it reminded me, do you need more information on how these are? These are all Greek letters, not SF, but the rest of them are Greek letters. This is the Greek letter alpha, which I usually draw as like a little fishy. The beta is like a bee with a tail. The gamma is kind of like a curly Y. Look up pictures on the internet if you wonder what they look like in real life. And this is the Greek letter epsilon, which is like a curly E. And then these are the Latin letters SF. I just told you this is like a curly Y gamma. Okay. And then this is lambda, the Greek letter lambda, and this is what we call half-life. And half-life is an amount of time.
It takes for half the nuclei to get.
Yep, the amount of time it takes. And we did talk about this last year. I assume you got that from your book, or maybe you did remember it from last year. But the amount of time it takes for a parent isotope to become 50% daughter isotope. And we use always those words. The unstable nucleus that began, we call the parent isotope, and the slightly more or maybe completely stable nucleus that results is called the daughter isotope.
It's kind of backwards.
I don't want to hear about your dating woes, boyfriend. Okay.
Funny joke in Raven.
What'd you say? Shh. What'd you say, Justice?
One funny joke that Raven said all year.
Yeah. Great job, Raven, with your one funny joke. And so, how would we measure this? What kind of units would we use to measure half-life, do you reckon? We'll read the definition carefully again. What kind of units would we use to measure this? Time, yeah. It's an amount of time. It's an amount of time. And every isotope has its own half-life. Cyrus, since you have your computer out, would you pull up a new tab and look up for me the half-life of, we talked about strontium-90 in the last chapter. Would you pull up the half-life of strontium-90 just so we have an example to talk about? And while he's doing that,
Would it be in like light years?
no, light years are a distance unit. What is it?
It's like years.
Just type up strontium-90 half-life. It'll tell you right away.
29 years.
29 years.
That's a lot shorter than I was thinking. I was thinking like millions of years.
29 years. So what we're going to do now, this is one kind of math that'll be interesting. And we will come back to the types and the math we do with them probably in a different video. But strontium-90 has a half-life of 29 years. And so if we're at, and what we usually do is we draw a,
Wait, what
I have these labeled. What do you think this one is going to be? Half-life. What's this one? Time. Can you guess? Percent parent isotope and percent daughter isotope. Okay, so the half-life, at half-life 0, how much time has passed? 0.
0. Or
What
no,
percent?
100%
It's 100% parent, and what percent daughter? 0% daughter.
So
What is the daughter isotope? Would you just mind telling me real quick? So our parent isotope is strontium-90. What's the daughter isotope of that?
Strontium, not
No.
How would you figure out the
We are going to figure out the half-life.
No, of the human cell.
Oh, human cell is not an isotope. We only do this for isotopes. What's up? Oh, well, just tell me a symbol, or what does it look like? Yttrium-90. Okay. So the daughter isotope here is yttrium-90. Shh. Oops, I was going to draw the letter 9 again, or the number 9. Is it just Y or YT? No, but we'll talk about why this is. Remember this one, actually. Write this one down, that it's strontium-90 is the parent and yttrium-90 is the daughter. And we'll use that as our first example when we talk about the kind of decay mode, the kind of nuclear radiation that is. But don't worry about that right now. Okay. So and then at half-life 1, how much time has passed?
1.
No. 29 years. How did you know that? He just guessed a number and it happened to be right? Nope. Because the half-life, one half-life is 29 years. Is this going to be the same for everything? No, this is specific to strontium-90. So if we did the same thing with uranium-238, this would change every time. How much of the parent isotope is there? 50% parent, 50% daughter. Okay? Now at half-life 2, how much time has passed?
Like 36 years. No, oh my gosh, that's so off.
Someone say the right answer, please. 58 years. How much of it the parent is left?
Or 0%.
Okay, we're having a. This is where everyone gets confused. Yeah, it's 25. We half this one every time. And then how much of the daughter is left? 25% daughter. At half-life 3, how much time has passed?
70 something, like 87.
87 years. How much of it is parent? 12.5%. And how much is daughter? 87.5. Good. We're going to do one more. 4. How much time has passed?
106.
Okay. Percent parent? No.
6.2.
I'll just give you this one, 93.75. Look, check it out before you go. I know the bell rings. Stay here for a second. These, look, this goes up by 1 every time. The half-life does. No, don't pack up. I want you to tell you this. Just wait. The time increases by however long the half-life was each time. This does what every single time? Divides by 2. And then this is just 100 minus this. Will this ever get to 0? Can I half it enough times? No. What do we call that in math? It approaches 0 but never gets there. What do we call that? Do you remember? It's an asymptote. It's an asymptote. It'll never, ever get to 0. Have a good day.